Good morning, dear students. Myself Shweta Prabhu, lecturer in physics, STMPU College, Honavar. In today's class, we shall see the topic regarding electromagnetic induction. Okay, it's the part 1 of the video. So, the contents which I am going to cover in the today's classes, that is regarding the introduction of the electromagnetic induction, experiments of Faraday and Henry, then magnetic flux and Faraday's law of electromagnetic induction. Okay. So, electricity and magnetism are the two different concepts. Okay. In the before the 19th century, here electricity was the different concept and magnetism was also the different concept. In the year 1820, Oersted discovered that electric current produces the magnetic field. So, one concept, what was that? So, electric current produces the magnetic field. Whether the vice versa condition is possible or a discussion arised. Later in the year 1830, Faraday and Henry performed the experiment that when we change the magnetic field, a EMF has been induced, hence the current has been produced. That phenomenon itself is called as electromagnetic induction. So, the phenomenon in which the electric current is generated in a closed coil by varying the magnetic field is called as what? Electromagnetic induction. Okay. The EMI, that is nothing but the notation which I use for electromagnetic induction. The generator, dynamo, transformers, the working principle of this is electromagnetic induction. We can't even imagine the single hour without the electricity. So this discovery of electromagnetic concept gave the huge revolution in the today's civilization. Okay. Let's see the experiment, Faraday's and Henry's experiment. The first experiment was current induced by a magnet. Okay. So in the diagram, you can see a coil. Okay. You can see here coil having number of turns, bar magnet, north and south pole. Okay. Here the coil is connected to the ends of the coil are connected to the galvanometer. So if there is a magnet, the magnetic field will be present, nothing but magnetic lines of force will be present. Okay. The first what they have done, okay, in this experiment, when the bar magnet was at rest, initial first statement, when the bar magnet was rest, there was no any deflection. Galvanometer, in the galvanometer didn't show any deflections. Okay. Next case, when the north pole of bar magnet is brought towards the coil, okay, towards the coil, galvanometer shows the deflection. Okay. Nothing but what we can say, if the deflection arises in the galvanometer, then current start to flow in the circuit or a coil. Okay. Next case, what happens when the north pole of the bar magnet taken away from the coil. Okay. Then also the galvanometer showed the deflection, but in the opposite side. Okay. So it has been also observed that if the movement of the galvanometer, that is if the movement of the magnet towards the coil moved faster and taken away faster, okay, if the bar magnet is took towards the coil faster and also taken away faster, then also the galvanometer shows the deflection. Okay. Suppose next case, when the reverse case, if instead of north pole, okay, if the south pole of magnet was brought near the coil or moved away from the coil, but then also the galvanometer showed deflection, but in the opposite direction, when we compare it to the movement of the bar magnet, that is north pole towards the coil, one of the face of the coil. Okay, so finally what we can conclude from these several cases, whenever there is a relative motion between the coil and the magnet, an EMF has been induced. Okay, if EMF has been induced, what we can say, the current passed through that, or current has been generated in the coil, or current start to flow inside the coil. Okay, so current is nothing but here induced current. Okay, here, so large induced EMF or current is produced in a coil if the motion, that is relative motion between the magnet and coil, is large. Okay, next, induced current lasts as long as movement of the magnet with respect to the coil continues. Okay, if the movement of the either coil or the magnet is continuous, then the galvanometer shows deflection. If both or any one of that is in the rest condition, okay, both are in the rest condition, then galvanometer doesn't show any deflection. Okay, next experiment, that is experiment 2, current induced by that current. Okay, so you can see here two coils S and P in the diagram, isn't it? So here S is the indication of the primary coil and P is, sorry, S is the indication of the secondary coil and P is in the indication of primary coil. Okay, so here either the inside the core, on the core, or in the air. Okay, so here wire has been wounded on the core and ends of the core has been connected to a battery. Okay, here if the circuit is closed, immediately the current starts to flow. Okay, current starts to flow, then magnetic field, magnetic field lines produced in that. Okay, so what happens in the another coil, where the coil has been connected to the galvanometer, so primary coil to the battery and secondary coil to the galvanometer. Okay, what happens when coil, that is primary coil, is moved towards the, okay, first case, case 1, if primary coil is moved towards the secondary coil, so galvanometer shows the deflection. Next, if primary coil is moved away, moved away from the, okay, if the primary coil is moved away from the secondary coil, then also the galvanometer shows the deflection, but is in the opposite manner. Okay, here one more thing we can do, we can fix the primary coil at the rest condition and move the secondary coil towards the primary coil, then also the same cases arise. If the coil, secondary coil, is moved towards the primary coil, galvanometer shows deflection, and if we also take away from the primary coil, galvanometer shows deflection. Okay, if both primary coil and secondary coil are in the rest condition, okay, primary coil and the secondary coil in the rest condition, so galvanometer deflection, the pointer needle, that is pointer, stops to 0, that is there is no any current in the circuit. Okay, that is, so finally what we can conclude or from this is that, so when primary coil moves towards or away from the coil, magnetic field or magnetic flux linked with the coil secondary coil changes, which causes induced EMF or current whenever there is a relative motion between the coil. Okay, just now what I have explained. The strength of magnetic field increases when iron core is placed in the coil. Okay, so here in this, if the core is replaced by the iron core, okay, if the core is replaced by the iron core, then the magnetic flux linked with the coil increases, hence the EMF will be increased. So finally what we can conclude, whenever there is a induced EMF, that is nothing but current has been induced in that when there is a movement between the current carrying coil and the conducting coil. So here current carrying coil means our primary coil, conducting coil is nothing but our secondary coil. Okay, understood? Next experiment. So current induced by the changing current. Okay, current induced by a changing current. In the diagram you can see on this single coil, in the one side of the core, primary coil has been wounded and another end secondary coil has been wounded. Okay, so here primary coil has been connected to a battery and a key, that is nothing but tap key, whereas a secondary coil is connected to the ends are connected to the galvanometer. Okay, it's the experimental setup for the whenever current induced by the changing current. Okay, it's the experimental setup. Let's see. If we close the key or press the key, okay, if we close or press the key, circuit will be closed. Okay, the circuit will be closed. So if you press the key, the circuit will be closed. So current start to flow here. Next, magnetic flux generated in the primary coil, and this magnetic flux gets in contact with the secondary coil. Okay, so this magnetic flux gets in contact to the secondary coil, hence the current start to flow in the coil, which indicates that galvanometer shows deflection. Okay, which indicated by the deflection in the galvanometer. Okay, next, if we release the key, then immediately the magnetic flux linked with the coil start to decrease. Okay, initially when the key has been pressed, the magnetic flux linked will be more. If we release the key, whatever the magnetic flux linked with the coil start to decrease automatically. Then the EMF induced across the secondary coil also decreases. Finally galvanometer shows zero deflection, then finally comes to rest. Okay, next, one more thing. If key is pressed continuously, okay, if we press the key, tap the key continuously, then also galvanometer doesn't show any deflection. Okay, if we open the key also it doesn't show any deflection. If keep the press the key, tap key, continue pressing it, then also galvanometer doesn't show any deflection. Okay, here suppose if we insert the iron rod, here iron rod, core with the iron rod, then we can see large number of magnetic flux has been linked to the secondary coil. Okay, large number of magnetic flux will be linked to the secondary coil, and finally the large deflection has been shown in the secondary coil. Okay, here there is no any relative motion between the primary coil and the secondary coil, but by pressing the key and releasing the key, we will get the deflection in the galvanometer. Okay, so finally from this experiment Faraday gives the statement. Okay, Faraday gives the statement. Before that, let's see what do you mean by. Okay, so this is regarding the setup. That is, what was that? On or off of the current in a coil changes the strength of the magnetic field produced by it. When the strength of the magnetic field linking with the coil 2 changes, coil 2 is nothing but our secondary coil. Okay, and EMF is induced in the second coil. So induction stops, that is when induction stops the change in the current, that is flux linking to the coil changes. Release of the key brings the current to 0. Okay, if you release the key, so what happens? The current start to decrease. So a decrease in the strength of magnetic field deflects the needle of the galvanometer in the opposite direction. Okay, or just now I have explained. Okay, the strength of the magnetic field linking is improved when wooden core is replaced with iron core, which makes galvanometer shows more deflection. Okay, it's the explanation regarding this experiment. Finally, what we can conclude? So coils have no relative motion, at change in the current in the primary coil induces an EMF in the secondary coil. Okay, next concept, that is magnetic flux. In the diagram you can see a area in which the magnetic lines, okay, this number of lines, field lines you can see. You know that which is this concept, this magnetic flux is similar to your electric flux. In the electric field, number of electric lines of force will be passing, whereas in this magnetic field, so number of magnetic lines will be passing through a particular surface. Okay, so magnetic flux through any closed surface is defined as total number of magnetic lines passing through the surface. Okay, magnetic flux through any closed surface is or total number of magnetic lines passing through the surface. Okay, so in the diagram, consider one small portion A, surface area A. So here n cap, okay, you can observe the diagram. So here n cap is the unit vector which is drawn normal to the plane. Okay, if it is a plane, so n cap is the unit vector normal to the plane. Next, theta has the angle between the unit vector and the uniform magnetic field. So, magnetic field is traveling in this direction. This angle gives you what? Theta. Okay. So, here n cap gives the direction, that is it is normal drawn to the surface, and theta is the angle between the n cap and the uniform magnetic field. Okay, so mathematically we can express the magnetic flux. The notation used for magnetic flux is pi or pi b. Okay, that is the dot product b dot a, where b is the magnetic field and a is the area of that particular. Okay, so b dot a, from the definition of dot product we can write ba cos theta, or we can say it's the product of magnitude of area and the product of one of the component of the magnetic field. Okay, one of the component of the magnetic field. Next, so here see here b cos theta is the component of the magnetic field normal to the plane surface. Okay, you can see this diagram. If it is a vector b, it has been resolved. Okay, one value. Okay, this value is theta. Then so here the component value is perpendicular to the unit vector, so the value b cos theta. Okay, so finally, magnetic flux for a given surface is the product of area of the surface. Okay, product of area of the surface and component of the magnetic field normal to the plane of the surface. Okay, how we can define the term? It's the product of area of the surface. Okay, it's the product of area of the surface and the component of the magnetic field normal to the plane of the surface. Okay, let's see the SI unit. Okay, so SI unit of magnetic flux is Weber. Okay, So WB, it's a scalar quantity. Okay, it's a scalar quantity. So we can also express this magnetic flux in terms of, okay, that is Tesla and meter square. Okay, magnetic flux, that is unit is 1 Weber is equal to 1 Tesla into 1 meter square. Okay, so 1 Weber is the amount of magnetic flux over a plane area of 1 meter square when held normal to the uniform magnetic field. Okay, so I will repeat once again. 1 Weber is the amount of magnetic flux over a plane area of 1 meter square held normal to a uniform magnetic field of 1 Tesla. Okay. Next, in the diagram you can see, okay, in the diagram you can see the cases. If theta value is 0, if theta value is 90 degree, if theta value exits other than 0 and 90 degree. So in the first diagram, okay, here maximum flux, okay, maximum flux, when the flux will be maximum if the the field is parallel to the surface. Okay, so if the field is parallel to the surface, that is if theta is equal to 0 degree, cos 0 means 1, finally the value will be maximum, that is vector should be, unit vector should be perpendicular to the area. Okay, so here magnetic field will be parallel to the surface. So magnetic field will be parallel to the surface. For the surface, magnetic field will be parallel and unit vector will be perpendicular to the, okay, unit vector will be perpendicular to the area, okay, surface area. Then we can say magnetic flux is maximum. Okay, let's see the second case. Here the magnetic field is perpendicular to the unit vector, that is theta is equal to how much? Theta is equal to 90 degree. Okay, cos 90 means 0. Okay, so the magnetic flux will be linking to a particular surface will be 0 if unit vector is, okay, if unit vector is perpendicular to the magnetic field. Okay, if unit vector is perpendicular to the magnetic field. Okay, if area has been rotated with say certain angle theta, then we will get flux as BA cos theta. Theta is equal to 0, flux maximum. Theta is equal to 90 degree, flux minimum, nothing but 0. If theta exits, we will get the expression as BA cos theta. Okay, understood? So by the experiment of Faraday and Henry, the final conclusion of all the experiments gives the Faraday's law. The statement is like this way: whenever the magnetic flux through the circuit changes, okay, whenever the magnetic flux through the circuit changes, an EMF is induced in it. The induced EMF lasts as long as whenever there is a change in magnetic flux continues. Okay. Second statement: the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with the circuit. Okay. So mathematically we can write E is equal to minus N d pi b by dt. Okay. So E is the notation used for the induced EMF. Okay. E is the notation used for the induced EMF. So d pi b is the notation used for the change in the magnetic flux. Okay. So what happens? There is a change in the magnetic flux linked with the loop changes. Okay. So if the magnetic flux in a closed loop changes, initially the magnetic flux value is pi 1, and after certain time the magnetic flux value is pi 2. Rate of change of magnetic flux can be written as pi 2 minus pi 1 divided by P. Okay, pi 2 minus pi 1 divided by P. Here E is the notation used for the magnitude of the induced EMF. Okay. Next, what does the Faraday's law states? If whenever there is a change in the magnetic flux linked with the coil, an EMF has been induced. See here, E is directly proportional to pi 2 minus pi 1 upon T. Okay. Here the expression has been written with a constant proportionality. What's that? E is equal to K into pi 2 minus pi 1 by T. Okay. Where K is the constant proportionality. If we substitute K equal to 1, how I can write the expression? E is equal to pi 2 minus pi 1 divided by T. Okay. E is equal to pi 2 minus pi 1 divided by T. Suppose if d pi b is the change in the magnetic flux in the small time interval. Okay. For the small time interval dt, d pi b is the magnetic flux changed. So we can write induced EMF E is equal to minus d pi b by dt. Okay. So here E is equal to minus n into d pi b by dt. Okay. So here in the formula n indicates total number of turns in the coil. Okay. In the formula, what does the term n indicates? Total number of turns in the coil. Okay. And the negative sign indicates, okay, so here induced EMF which has been generated, which always opposes the change in the magnetic flux linked with the circuit. Okay. So here negative sign explanation is given detailed by the Lenz law, which we are going to study in the next session. Okay. So finally here in the today's class we have learned regarding the introduction. Next, how does the Faraday and Henry set up the experiment, and finally they gave the Faraday's law true statement. Okay. Thank you.